Not for this one, but I can hold it. It's fine. Oh, I have a pocket coat. No, girls' clothes don't have pockets. I can just, I think I'll hold. Should I just put it on my coat here?
Because in full screen mode, the mouse is there.
Oh. We can come back to full screen. Yeah.
Okay.
Yeah. It's not showing there. So I think that's okay.
Hello and good afternoon. Sorry for the slight delay in starting, but we are all set now. And welcome to another session for Asset. And we are very lucky to have prominent speakers here today. I'll give a brief introduction. They're going to speak about unlocking the mysteries of the universe with the Deep Underground Neutrino Experiment. Dr. Soujanya Gulapini is a senior scientist and neutrino group leader in the Los Alamos National Laboratory, LANL. She earned her PhD from Wayne State University, followed by postdoctoral position at Kansas State University, and then working in LANL since 2019. She was a faculty in the Department of Physics and Astronomy at the University of Texas, Knoxville before. She is an experimental particle physicist, and her current research focuses on study tiny particles called neutrinos, and she's going to talk about the experiment today. And we also have another speaker with us today, Professor Lucy. I'm sorry if I'm pronouncing it slightly wrong. Yeah. He has been working in the field of experimental particle physics at DESY in Hamburg, at Fermi National Laboratory in Chicago, the National Laboratory Nationale and the Franceschetti, LNF, at the Institute of National del Pesca Nuclear. I'm very sorry if I'm mispronouncing the institution's name. Yeah. So without any further ado, I request Dr. to please start with the topic.
Okay. All right. Thank you. Thanks for that introduction. I'm Soujanya, like I was just introduced, and Sergio is sitting here. So I'll go first, and then Sergio will go after me. First of all, thanks to the organizers and Bipul and Gagan Mohanty and others who have invited us. We're here at TIFR today for a workshop in order to discuss India's contribution to the DUNE experiment. You're probably, the DUNE movie is probably more popular, but I'll tell you the experiment is as exciting and adventurous or even more than the movie. So I'll talk about DUNE today. Sergio and myself were co-spokespeople of DUNE, of this large international collaboration that is set out to do exciting physics. So let me start with why study neutrinos. There are many reasons. I'll highlight a few. The first thing is, we're all curious about how the universe has formed, right? And our way to understand how the universe has formed and evolved is to study the particles, that have formed at the time and are still now all around us. And neutrinos are one of them. So the neutrinos formed during the Big Bang, we refer to them as relic neutrinos. You may be surprised, they're very pervasive even today around us. So studying them will help us, give us insight into the origin of the universe. The other reason to study neutrinos is when you have the most violent explosions in the space, could it be big star exploding, sun that emits a lot of radiation, you have a ton of neutrinos that come out of it. For example, when a supernova occurs, neutrinos carry 99% of the explosion energy, and that's your way to understand how this process happens. And then sun, like I just mentioned, sun emits neutrinos quite a bit, actually. You can see the flux that I've mentioned here. So 10 power 38 neutrinos per second produced by sun that reach around us. So neutrinos are all around us. Right now, through my thumb in this room, there's billions and trillions of neutrinos that are surrounding us. I spoke about very big things that are happening that produce neutrinos, and we can use them to study those phenomena. But neutrinos are also produced in very small things as our nucleus. It goes through certain decays that emits neutrinos all the time. So you can also study about nucleus. And even something like everyday item you see in your kitchen, bananas emit neutrinos because they have a very small amount of radioactive potassium. So you're all getting 10 power 6 per day, from bananas if you have them at home. So if you look at, I mentioned a few sources. If you look at, the very many sources that produce neutrinos, as shown on this plot, there's overwhelming number of sources. You have supernovae, sun, as I mentioned, Earth emits neutrinos, reactors emit neutrinos, neutrinos are produced in atmosphere, cosmic origins, and human-made neutrinos come from accelerators, as many of you know. So, this means that when you have these many sources, they span wide range of energies. You're going from very small energies to very, very high energies. And in order to study the diverse sources of neutrinos, you need a wide spectrum of experiment and technologies. That's where a lot of opportunities that come our way for the students and postdocs sitting in the audience, something to keep in mind for your future careers. Okay, standard model of elementary particles. This is like our periodic, this is similar to the periodic table in chemistry. We keep going to refer to this standard model. So this is the theory about fundamental ingredients of matter and how various forces and particles interact. And you can see we have various fundamental particles here. Leptons, this category. Maybe the most familiar particles for you is electron, right, that you may have heard in your education. Electron, muon, and tau are the leptons. And then we also have corresponding neutrinos. There's 3 types of neutrinos. One way to look at this lepton sector is that the neutrinos are the inseparable cousins of electron, muon, and tau. These are charged. These are not charged. I say inseparable because whenever you have a neutrino, electron neutrino, you have an electron coming out. Whenever you have a tau neutrino, you have a tau coming out. That's how we tend to detect the neutrinos that I'll talk later. So we know there's 3 types of neutrinos. Without going too much into the details, this has been experimentally verified by experiments. Confirmed that there's only 3 neutrinos that couple to what we call the Z boson. They're neutral, like I said, they have no charge, and they're extremely weakly interacting. To give an example, if you take a neutrino coming from the sun, which typically has MeV scale energies, it takes about 10 light years of length. A light year is what, 1 trillion miles, right? So you can understand the scale. They're not very sociable at all. They don't like to interact. So a big challenge when we do neutrino experiments is how do you make them interact? How do you make them talk to your detectors, right? So we can study them. The tricks we have up our sleeve is in order to make neutrinos stop and interact so we can study them is you put a target that's really, really dense. You build huge, humongous detectors. I'll show some scales later on. And then you fill that detector with something very, very sensitive. That increases the probability of neutrinos interacting and you studying them. According to the standard model that I just showed, neutrinos have 0 mass. And this is not until recently, this is what people thought. Before we go back to the mass of the neutrinos, let me mention how we came to discover neutrinos. These are the observed energies. Beta decay, the nuclear beta decay is the process that I've shown here. If you plot the energies of the nuclear beta decay, what you expect is just this one peak. This is when we didn't know neutrino was there. You have a proton converting to a neutron, and then you have an electron coming out, in which case it's one particle, so we expect to see one peak. However, what we observed is this continuous spectrum, and that was a big mystery at the time. And then Pauli came in after that and said, well, in order to explain this, there must be some other particle that's coming out, right? That's why you see this, instead of a sharp peak, you see this spectrum. And then he said, I've done a terrible thing. I have postulated a particle that cannot be detected, because Pauli knew this very teeny tiny particle that has very tiny mass would be very hard to detect. And he was right. This is in 1930, 31, and 25 years later, Reines and Cohen, Los Alamos lab, they finally detected the first neutrino from a nuclear reactor, and that won the Nobel Prize in 1995. I'm sorry, the transition is taking too long. And then what else we found was that, neutrinos, I said there's 3 types of neutrinos, and they have this weird behavior of morphing into each other, to different types. So if you, think of 3 flavors of ice cream, right? Vanilla, strawberry, and chocolate. You start as vanilla, but if you travel it's a long distance, you become strawberry or chocolate. So this is a very interesting phenomenon referred to as neutrino oscillations. And for that to happen, neutrinos need to have mass. Very tiny mass, but nevertheless, they should have mass. And I just said 2 slides before, standard model has 0 mass for neutrinos. And, this article came out when that was first observed. Mass found in LGZU particle universe may never be the same. To some extent, this is true, because the fact that neutrinos have mass did revolutionize the field in many different ways. And this is very recently, we're talking about 2000 is when this discovery has happened. And that has opened door to many, many, many exciting things. Let's see. So what are neutrino oscillations? Like I just said, if you have a source of neutrino, let's say you're producing a specific type of neutrino, a muon neutrino, you let it travel a long distance, you end up detecting a different flavor of a neutrino. So this phenomena of one flavor changing into another is what we refer to as neutrino oscillations. And this is a complicated phenomena to explain, but the way to look at this is that this is the quantum mechanical evolution of states that is determined, and then that evolution determines what you measure. Simple way to look at that is, you produce neutrinos in specific flavor states, specific flavor of an ice cream, for example. As they travel as a superposition of states, which we refer to as mass states. And then at a given point in time, you detect them, they interact with your target, and then you detect them as, again, one flavor of your ice cream. So this is, in other words, this is the quantum mechanical phenomena happening at a terrestrial scale. Very, very intriguing and interesting, if you think about it. Okay, detecting neutrinos, like I said, whenever a particle is neutral, it doesn't have charge. It's very hard to detect them. Charged particles leave visible traces. It's easy. With neutral particles, you sort of have to, imagine where they would have interacted and what comes out of it. So with neutrinos, like I said, if you have a given, if you have a chocolate neutrino, you get chocolate out, right? So that's your lepton, the cousin. So this is how we detect. We cannot measure the flavor of the neutrino directly, only through once they interact and only through the outgoing lepton, the cousin that comes out. And there's different types of those interactions. There's charge current interactions where there's exchange of charge. There's neutral current interactions. And you can also measure these oscillations in 2 ways, appearance and disappearance. For example, this is just an illustration of how we do these measurements. For example, you can look for a deficit of the original flavor. For example, you can say, okay, I have produced 100 muon neutrinos, and then you can look here how many of the muon neutrinos I have lost. If you started with 100, you measure 76, right? That's the disappearance measurement. An appearance measurement is you look for the new flavor, the excess of the new flavor. So for example, if you start with 100 muon neutrinos, you measure 25 electron neutrinos. So we do both kinds of measurements, and they're sensitive to different physics. Since then, since that concept of oscillations and the first evidence we saw, there's been overwhelming evidence for neutrino oscillations, not from one experiment, not from one source, from a number of experiments and a number of sources. I have highlighted 3 here. This is a measurement of the oscillations. In these plots, the one thing you'll see is that there is a prediction without oscillations. For example, in the case of atmosphere, it's this one. And then there is a prediction, the green one, with oscillations. So if oscillations were to happen where neutrinos are turning into different flavors, you always measure the one with oscillations, this prediction, right? That's why you see two curves here. And the black dots in all these plots are data, and you see them matching to the prediction with oscillations. This is from atmospheric neutrinos. This is from human-made accelerator neutrinos. This is from nuclear reactors. So we saw overwhelming evidence for neutrino oscillations, and that's the 2015 Nobel Prize that was received for this. All right, so neutrino oscillations are a big deal today. They make fantastic probes to probe in, for a wide range of physics that you can explore, the Big Bang cosmology, dark matter, the question about why the universe is matter dominated, even understanding, fundamental symmetries and violation. There's almost every topic you can probe with neutrinos. So very quickly, some math, so because it's relevant for later. If you assume there's only two flavors of neutrinos, right? Just two neutrino system, you ask what is the probability that I start with one flavor and end up with another flavor, right? And that's this equation, and that's this sinusoidal curves that you see. Basically, this probability of oscillation has two terms, an amplitude and the frequency. And the way we measure oscillations is as a function of this parameter called L over E. L is the distance between the neutrino source and your detector. E is the energy of the neutrino. If you build your detector very far away, 1,000 kilometers or more, we call that long baseline. If you put your detector a kilometer or so within the source, we call it the short baseline. We measure oscillations as a function of this parameter, and then we characterize them by these terms, delta m square, which is the mass square difference, and then the mixing angle, which is the sine square 2 theta. And that's also illustrated here, as you can see. Okay, to the more complicated picture, for a 3-neutrino oscillation scenario, if you take the flavor states and the mass states, remember I mentioned this before, the way this mixing happens is through this mixing matrix. This is analog, if you're familiar with quarks, this is similar, analogous to CKM matrix for quarks. But if you expand that mixing matrix, this is what you get. We don't need to get into the details of it, but you can see that the different terms of this matrix can be sensitive to different sources of the neutrinos and the energies that you use in your experiment, which is what we have done over the last decade. And then, we have values for all of these. Delta CP, we still need to measure, which I'll get into in a bit. If you look at this mixing matrix, we have 3 mixing angles, these 3 angles that spread across this matrix. We have a complex phase that we refer to as delta CP, and then 2 mass square differences. And CP stands for CP violation, charge parity violation. I'll explain that in a bit. But the important point here is if you look at this matrix, if theta 13, this term, if theta 13 is not 0, then this whole term becomes non-zero, right? So that's what opened the door to CP violation in the neutrino sector. And even the measurement of theta 13 is very recent. So the importance of delta CP comes in because it can shed light on the question that we're all very keen to know is why we live in a matter-dominated universe. Okay, so coming to that question, we know that during Big Bang, equal amounts of matter and antimatter, if they canceled, there would just be light and we wouldn't be here today, right? But something canceled that cancellation. So the small amount of matter persisted over antimatter at the beginning of the universe. And we don't know what processes made that happen, right? What processes can lead to that observed asymmetry. I call this the holy grail for particle physics that we're all out after to get an answer to. So what is CP violation? Charge, you all understand, positive to negative, right? Charge symmetry. parity is the symmetry, we call it left-right-handed. The easier way to understand is spatial symmetry. And then CP is a combination of the two. So if electron is your matter, positron is your antimatter, right? So we tried to look for this CP violation. So for universe to have become matter dominator, CP violation must have happened. The question is where it happened and how much it happened to see the symmetry that we're seeing now. So we tried to look for this CP violation in other particles, like quarks, for example, but in order to explain the absurd asymmetry, we need to see much more than what we have seen. And neutrinos is a place where we haven't explored this, and then that's where the DUNE experiment is focused on. The other question with neutrinos is the neutrino mass hierarchy. I mentioned before there's two mass square differences, and you can arrange them in two different ways. One is referred to as normal mass hierarchy, other is inverted mass hierarchy. So in other words, to put it in a simple way, we don't know which neutrino is the lightest, which neutrino is the heaviest. And that's determined by this mass hierarchy. So that's an open question as well. So I only mentioned a couple of the questions that are open, but there's still a lot we don't know. We've been studying neutrinos for almost a century now, but the number of questions we need to answer is a lot more. So within the standard model, 3-flavor mixing, these are all the open questions. We don't know the absolute mass of neutrinos. Like I said, we don't know which neutrino is the lightest. CP violation in neutrinos, these are all open questions. But there's also new physics that neutrinos are sensitive to. One question is, we said, we have experimental confirmation. There's 3 types of neutrinos, but we have seen many tantalizing hints that there could be more flavors of neutrinos, maybe 4th or a 5th. So are there more than 3 neutrino flavors? We don't know the answer to that. There's also other new physics that neutrinos are sensitive to. So there's a lot of ground to cover, and there's various categories of experiments focused on answering a given question. For example, absolute mass of neutrinos, this is usually probed by what we call direct mass measurement experiments like Katrin, for example. A lot of these questions in green, the mass hierarchy, the CP violation by long baseline experiments. The question about sterile neutrinos or additional flavors is short baseline experiments. So today, as we go into DUNE in just a bit, our focus will be on the long baseline experiment, which is what DUNE is. I'll just leave with the thought before I dive into DUNE that completing the story of neutrinos is not one experiment, it's multiple experiments. Like I said, you have these categories of experiments trying to bring each piece of the puzzle, right? And that puzzle needs to come together. So this table is an attempt to sort of summarize, how many the categories of experiments are trying to answer the same question. And this complementarity and synergy is something that's really needed in order to complete the story of neutrinos. All right, long baseline experiment currently, in Japan, we have T2K and Hyper-K. T2K is running, taking data. Hyper-K is a future experiment like DUNE. In US, there is NOVA, MINUS Plus. DUNE is your future experiment. And you can sort of see their baselines, right? How far away the detectors are from the neutrino source. For the ones in US, the beam comes from Fermilab. One is in Sudan mine, one is in Ash River. DUNE will be in South Dakota at the Homestake mine. And then in Japan, you can see the baseline is short. This is 295 kilometers. And these set of experiments are good. Talking about the next generation one, which is DUNE and Hyper-K, I just mentioned that the baselines are very different, right? DUNE is 800 miles or 1,300 kilometers. Hyper-K is 295 kilometers. There are other differences, the size of the detector, the target material they use. This is liquid argon. This is water. DUNE's beam is wideband beam. Hyper-K is narrowband. I think this complementarity is key. We have seen this with LHC experiments, right? When you make a major discovery, you need cross-confirmation, and that's where the importance of both of these experiments comes in. It's both powerful, but also essential in order to provide cross-confirmation. The timelines are a bit different. Hypercase starts 2028. That's when it's expected to start. And for DUNE, the first beam data, we start towards the end of the decade. The beam data comes in early 2030s. Okay, diving into the Deep Underground Neutrino Experiment, DUNE. Like I mentioned, DUNE is a big international experiment. There's over 1,400 collaborators from over 35 countries. And we also have CERN as one of our big partners in DUNE. The DUNE experiment, the basic setup is this, a megawatt scale beam. And for that, there's a lot of accelerator upgrades happening at Fermilab, and India is a big partner in some of those upgrades. So the megawatt scale beam comes from Fermilab, travels 800 miles. There is a near detector that we'll put here that sort of characterizes the incoming flavor and spectra. And then the neutrino beam goes through the near detector, 800 miles, travels in Earth, in matter, in other words, and then it meets a much bigger detector, a mile underground at the SURF lab in South Dakota. SURF is Sanford Underground Research Facility. And this setup is key for many reasons, which I'll mention in a bit. The near detector it's multi-technology near detector, which Sergio will talk more about. The FAR detector is one of the biggest liquid argon detectors that we'll ever build. And then the site facilities at the near and far are provided by what we call the Long Baseline Neutrino Facility, or LBNF. The physics of DUNE is very rich. I mentioned CP violation, mass ordering, but then the main goal is to complete the picture of the neutrinos with precision measurements of oscillation parameters, and then neutrino astrophysics as well, and then beyond the standard model physics. And I'll point out here, since many of our Indian colleagues are here, when it comes to the physics of DUNE, India is making many important contributions in the areas of theory, simulation, reconstruction, data analysis, and those are all valuable to the collaboration. Okay, so DUNE oscillations, we start with primarily a muon neutrino beam. It's never 100% pure. There is some contamination of electron neutrinos and other flavors, but it's primarily a muon neutrino beam, and then that goes through Earth, the 1,300 kilometers, and you can see, in terms of the oscillations, you have dominant oscillations, but we are interested in the subdominant oscillation of muon neutrino converting to electron neutrino, oscillating into electron neutrino. Although it's subdominant, this oscillation is actually very sensitive to rich physics, and that's what we're interested in. All right, so we look for excess of electron events. So I mentioned the appearance and disappearance experiment. So DUNE is an appearance experiment. We look for an excess of electron events. And you can see at the L over E of 500 kilometers, you can see the sort of excess we are looking for. It's challenging, but if you detect it, you're very sensitive to all the physics that you're trying to do, including CP violation. So this is a NUE experiment, I'll say, in matter, and that's important to emphasize because the physics is very different when it goes through Earth. It's interactions in matter. So in order to make neutrinos go through Earth, I mean, you can't steer neutrinos directly, right? Pions and kaons produce neutrinos in the way we produce the neutrino beam. So you kind of magnetically steer those. And then once neutrinos are produced, they go straight. They don't interact, right? So they go to your detector. In order to have this steering of neutrinos, there is an artificial hump that's at Fermilab to make that happen. So on the beamline and accelerator upgrades, I won't go into too many details, but the ultimate goal for DUNE is that we have a greater than 2 megawatt beam by early 2030s. And for that, there is a bunch of upgrades that are planned with the Fermilab accelerator. One is called the PIP2, Proton Improvement Plan. This is an upgrade of the Fermilab to reach the 1.2 megawatt beam. And then it does, as part of that upgrade, it creates a platform for next generation upgrades, which are referred to as ACE-MIRT and ACE-BR. ACE stands for Accelerator Complex Evolution. And you upgrade various things as part of the eights, main injector capabilities, target systems, and so on. And ultimately, with a combination of PIP2 and A's, you get a greater than 2 megawatt beam. And as I highlighted here, India is a major partner on PIP2. In fact, this visit is an extended visit where several people from Fermilab are coming here to TIFR and BARC to discuss PIP2 activities. Okay. The reason we are interested to have the DUNE NUE appearance in matter is because they play an important role. If you take that, remember the very simple math I showed a few slides ago. If you take that, go a bit deeper into that, you'll see that a NUE appearance in matter will be sensitive to rich physics. This is the math that goes there. And you can see there's various terms that make you sensitive to the mass hierarchy and the CP violation, and that's what we're interested in. And you can see the spectra of the nu mu to nu E oscillations, where both for neutrinos and antineutrinos, where you get sensitive to various oscillation peaks. And then the reason for that is, when neutrinos travel to Earth, they travel through matter, right? Electron density in matter is what causes the asymmetry through a process called forward weak scattering that's shown here. And the sign of that depends on the neutrino mass hierarchy, whether it's normal ordering or inverted ordering that I mentioned before. So the strategy for DUNE is you first produce neutrinos, you send it through 1,300 kilometers to South Dakota. Then you switch the polarity of the beam and you send antineutrinos. And then you compare the probabilities of the neutrino oscillation and the antineutrino oscillation. And that's what makes you sensitive to the CP violation. Okay. So, for CP violation and mass hierarchy, what can DUNE achieve? So if nature is kind, by which I mean if the CPV is maximal, then this plot on the left is mass ordering, mass hierarchy. The right is the CPV sensitivity. You can see if you look at the CP sensitivity as a function of number of years, you'll see that if nature is kind, we'll get to greater than 3 sigma significance in about 3.5 years. For mass hierarchy, you get to the discovery sensitivity in just 1 year. But if nature is unkind, which means that you have to scan a broad range of CP values, right? For mass hierarchy, we're still pretty good. You get to the discovery sensitivity in 3 years. It just takes a couple more years. But then for the CPV, you'll see that it takes about 15 years to cover about 75% of delta CP at greater than 3 sigma. So we don't know, is nature kind or unkind? That's part of this process. I mentioned before that DUNE is also great at for astrophysics, neutrino astrophysics. Especially, DUNE has the unique capability for electron neutrinos through this process called charge current NUE. If you look at these cross-section curves as a function of neutrino energy, you'll see that for NUE on the argon, your cross-section is higher, and the capture of electron NUE. Capture of neutrinos on argon is one of the most sensitive channels that you have. And if you take non-argon experiments, like HyperK that use water as the target, this is highly complementary because they're traditionally sensitive to inverse beta decay. And DUNE is unique that it's sensitive to the NUE capture on argon. And if you look at the supernova events as a function of time, the early development of the signal in this region, what we call neutronization, that's sensitive to the mass ordering of neutrinos. So it's you look for supernova neutrinos, but that's also helps you understand what's the ordering for the neutrinos. So there is synergy there. And then in terms of new physics, I won't go into these complicated plots, but both the far and the near detector of DUNE, they're sensitive to rare processes. The far detector, especially for cosmogenic origin, and then near detector for the processes in the beamline. And, other neutrino interactions. Okay, so we'll build DUNE in two phases. Phase one, you have a near detector where you have a liquid argon-based near detector, a muon spectrometer, and then what we call SAND. It's an on-axis beam monitor. And then for the far detector is built as 4 detectors. In the first phase, we'll build 2 of them, and then the beam would be 1.2 megawatt beam. And then in the second phase of DUNE, which is when we complete the experiment, the full scope of the experiment, we replace the muon spectrometer in the near detector complex with the gaseous argon TPC, gaseous argon detector, and then we install the other 2 far detectors for the far detector complex, and then we take the beam intensity to greater than 2 megawatt. That's the full scope of DUNE. With phase one, we are still statistics limited. So that's where the importance of increasing the beam power and the fiducial mass comes in. So you're now, you reach your precision, increase your statistics and get the systematics at the level you want. All right, on the far side, like I mentioned, the far detector of DUNE will be at the Sanford Underground Research Facility in Lead, South Dakota. It will be 1.5 kilometers deep underground in the Homestake mine. This is probably, people are familiar with this. This used to be a gold mine in 1889. No more gold, we're told. We have done a lot of digging. We didn't find any. There is another legacy to that. This is also called the infamous neutrino burglar. This is the home of Ray Davis's solar neutrino experiment. This is when we didn't know neutrinos oscillate. So when they tried to measure the flux of the solar neutrinos that are coming from sun, their expectation, their measurement was less than what they expected because the neutrinos were oscillating into another flavor. So, but at the time we didn't know. So this was referred to as, this site was stealing neutrinos somehow. We now know it's the oscillations. All right, on the far detector, like I mentioned, there's 2 caverns, 4 detectors, and that gives you flexibility in the design. The wide deep underground location, cosmic rays are a major background to us. That's why surface detectors are challenging for us. A challenging background for us, and that's why the option to go deep underground, and you get a huge reduction in terms of cosmic ray backgrounds at the 1 mile underground location for DUNE. So as of January last year, the excavation of the massive underground caverns at SURF has been complete. This is a huge milestone for us. There's final safety checks and logistical things that are being looked into right now, but we'll get the occupancy in January next year. And this is one of the most expensive digging, I can say. The amount of rock that was excavated, the amount of money that went into it, which is close to $1 billion. Who knew excavation would cost that much? So the DUNE far detector, like I mentioned, it's 2 caverns, 4 detectors. Each 14 kiloton capacity detector modules. And the fact that we have these sort of factorizable offers the flexibility in the design for us. This is just to give you a sense of scale, this is the size of one 17 kiloton module. This is 66 meters long, 19 meters in terms of width and the height. There's a pretty large, gigantic detectors. For the 4 detectors, there's sort of a strategy we are following. The first 3 far detector modules will be liquid argon based, the liquid argon time projection chambers. The 4th one is a module of opportunity where both liquid argon and non-liquid argon options are being explored. To the question of why liquid argon, there are many great properties of argon. It's dense, it's abundant, easily ionizable. You get a lot of charged signals, right? It's highly scintillating, so you all can also detect light in addition to charge. So all those are great properties. But I would say the real reason we went with argon is that it's cheap also. Maybe it's not $2 anymore, given the Ukraine-Russia crisis, but still much cheaper than anything else you can go with. If you can build with krypton or xenon, fantastic, but that's your 4 billion right there. You went with it. So how does a liquid argon TPC work? This is just a quick animation. Neutrinos come in, they interact with argon in your detector. They produce charged particles that ionize argon, right? And those are the ionization electron signals that you collect on this very sensitive mesh that you see that are your wire planes. And then, you have a scale segmented anode wires. They give you excellent resolution. You measure the drift time, you get your 3D image. That's in a nutshell how a liquid argon TPC works. But the outcome of these detectors is actually exquisite. These are events with unprecedented detail, right? These are like your digital bubble chambers in some sense, very imaging detectors that offer calorimetry. And then you can even see really small things like delta rays, the small energy blips and other point-like depositions that you see. The challenge is how do you mine this very exquisite event displays with all this information, right? That's another challenge that we're working on. So the first FAR detector will be a liquid argon TPC. It will be a horizontal drift liquid argon TPC. As the name suggests, the drift is in the horizontal direction. You have your cathode, anode. Like I mentioned, when you have ionization electrons, they drift horizontally and they get deposited and collected on your wire planes. The first FAR detector will be segmented because you need to hold purity for long drifts, which is a challenge. Now we can do better, but this is the design at the time that we're following with. You have 4 drift volumes here for your first FAR detector, very high voltage. So there's many R&D and technical challenges that have been dealt with for us to come to this stage. How do you keep the high voltage stable in liquid argon? How do you make sure there's no shorts and other issues? But that has been demonstrated, that success has been demonstrated with a lot of prototypes. FAR detector 2 will be a vertical drift LArTPC. Here the drift is vertical, but you can also see the drifts are longer. Instead of 4 volumes, you have 2 volumes here. You have your cathode in the middle, anode at the top and the bottom. The readout is charge strips instead of wires. That offers more advantages and flexibility. It's costless. There's several advantages in this direction. The high voltage needs to be higher though, because you're drifting the electrons longer. So we have tried to demonstrate all these technologies at the CERN neutrino platform. This offered full-scale validation of our design, installation, commissioning, operations, and analysis to a great level. There are 2 prototype detectors. One is a proto-DUNE horizontal drift that you see here and a vertical drift. And these detectors were built and commissioned. The vertical drift will be commissioned as we speak, but the horizontal drift ran twice successfully. And then the beam at CERN is a particle beam. You get various particles. These are 770-ton prototypes. They're not small detectors. They're actually big detector prototypes. So proto-DUNE horizontal drift, this is the largest detector constructed to date that ran successfully. The phase 1 ran 2018 to 2020, collected 4 million events. Phase 2 ran last year, also finished successfully. And then the vertical drift, this is commissioning as we speak. And all the detector components are installed and will take data later this year. This is just a slide to highlight the success of the proto-DUNE phase 1. There is this paper that came out on the first results from this run, but there's several papers since then on hadron argon cross sections, detector calibrations and reconstruction and so on that came up. We saw excellent performance when it comes to noise, purity, high voltage stability, and so on. For the phase 2, like I said, the horizontal drift phase 2 ran successfully last year. It's concluded, analysis ongoing. From LANL, I would say, from our consortia, this is the first time we installed calibration systems on the phase 2 horizontal drift detector and took data successfully. Vertical drift completed installation and commissioning has started. We'll take data later this year. You can see some pictures of that commissioning. And then for the phase 2 FAR detectors, which is your FAR detector 3 and 4 out of the 4 modules, there's a lot of R&D going on. This chart sort of summarizes both in terms of detecting charge, how well we can improve the coverage, the signal to background ratio and so on. And also in terms of light detection, there's a lot of R&D. I won't go into all of the details, but each name mentioned here is a technology path that is being pursued. These are all argon R&D, argon-based R&D for liquid argon TPC, but there is also water-based liquid scintillator, such as the THEA option that is being considered for FAR detector 4. This is one slide snapshot of the active R&D and the prototyping that's happening for phase 2 for FAR detectors 3 and 4. So you can see everybody is prototyping at this stage and improving the technology constantly, and also assessing the performance as we go for the phase 2. There will be a future proto-DUNE run as well for phase 2 technologies. Okay, for the near detector, very quickly, this will be located at Fermilab, like I said before. It will be 60 meters underground. It will have multiple technology, like I've mentioned before. One is the SAND. This is a tracker, ECAL, on-axis magnesite beam monitor. And then you have the liquid argon near detector, the muon spectrometer, that is part of the phase 1. And then the interesting thing with the near detector is that we have this DUNE prism concept where the ND-LAR, the liquid argon near detector and the muon spectrometer, they can move off axis up to 29 meters, as you see here. The engineering for that to happen has been designed. And that will be very useful in constraining uncertainties related to flux, for example. From phase 1 to phase 2, the muon spectrometer will be replaced by the gaseous argon detector, which I won't go too much into the details. There is a lot of R&D happening. The main challenge is, how do we operate these detectors at high pressure, 10 bar pressure, and keep the gain at the level you want? And then for the non-argon options, there is various opportunities being pursued. For example, can we add additional targets in the SAND detector or the gaseous argon detector, or consider dedicated non-argon near detector targets? All right, so the key takeaways are that this caverns at CERN excavated January 2024. We'll have occupancy early next year. This is a picture of the cryostat steel that arrived from CERN and other places to SURF, and it's sitting in the warehouse ready to be installed. The near detector design is complete. We're working towards the next set of milestones. This schedule here sort of shows what I said. The cryostat installation starts January next year, and then the detector installation will proceed from there. Right, this is a picture of our May collaboration meeting. I couldn't be there, but this is a very lovely picture that I wanted to share with you all. So that's all. And then Sergio talk on the near detector. Sorry, that took longer.
Yeah. I promise I will not keep you long. As Soviania has said, I mean, one of the good thing about DUNE is that we are essentially doing everything, measuring all what we can be measured in this matrix of oscillation, all in the same experiment. And that we do it because we look at appearance, disappearance at the same time. We have a wideband beam, so we can follow all oscillation period. And this, of course, is a big advantage. You ask, why not everybody is doing that? It's because it's more complex. And because you have just to reconstruct very well the energy of the neutrino, and you have just to keep your systematics very much under control. And that's why it gives you some advantage in some cases and some disadvantage. Because the fact that you can follow this all oscillation period allows you just to make chunks in the energy and just look how the oscillation behaves in that chunk. And this is very good because it can resolve degeneracy. Whereas if you simply are looking at this biplot, you plot the number of neutrino electron, anti-neutrino electrons, these ellipses are becoming very flat, and the phase can go inside your error almost in any place. And this is also a good thing because we do that. This is an exercise. We have divided it in only a small number of pieces. But if you do it in the real life, we can get up to very many energy beams, and we become very, very sensitive to this oscillation. It's also good because, for instance, this could be a way in which you look at the signal if there is new physics. For instance, if you do three energies beams, and for any reason this CP phase is sensitive to energy, you will be seeing it moving in different places, and you will be sure that you have new physics. In order just to do that, you need, I go fast, you need just to have to control all the systematics. And the only way in which you control the systematics is that you have just to have a very powerful over-designed near detector. Because nature is not good. There is this legend that nature is good. Nature, no, is there just to trick us. And that's why we designed a complex which has different functionalities and which will be evolving in time. This complex, as Soviania has already said, has two fundamental parts. One part which is done by a detector which is liquid argon plus a muon spectrometer, which moves. And this is a single detector functionally, because the liquid argon is needed because we want just to have a target which is the same and the technology which is the same as the far detector. But we cannot make another far detector in the near detector. We take advantage of the fact that we have much more rate there because we are close to the source. And so we need another detector which tells us all the particles which are escaping the muons, essentially. And then there is another part which stays always on axis. And because we have just to control all the uncertainties. And the uncertainties are coming from the fact that we know we have large uncertainties on the neutrino cross section on nuclei, which we cure partially having the same material in the near and the far detector. At the first order, we cancel it. And the other thing we have just to control the flux. And because, as a matter of fact, we measure the product of the flux times the cross section, and so in order just to control that, we have just to control the flux, and we have just to control the energy scale. This is the other part. And this is needed because all these oscillation parameters are a function of energy. And if you are off scale, of course, we measure a totally different number. And this, just to give you an idea, all the current experiment, after many, many years, and many have systematics which are of the order of, depending how optimistic you are, between 5 and 7%. We need, in order just to measure with precision what we do, we have just to go down between 1 and 2%, which is a big step. Okay, so we have 3 detectors, I told you, and these 3 detectors are somehow peculiar, especially the one of liquid argon, because in this case, neutrino interaction are very rare, but if you have a 1.2 megawatt beam not so far away, they are big. There is a big number of events. So a liquid argon is beautiful because it's an electronic bubble chamber, but is slow. So essentially, what will happen in real life is that in 10 microseconds, you get about 20 neutrino events. And if you would use very long drift, the electron drift in liquid argon is pretty slow, is order of milliseconds. You will have essentially a thing which will be a mess because you cannot reconstruct. The way for solving that is just to make shorter drift distances and read this drifting electron with a 3D intrinsic lecture with pixel. Essentially, as it is done in the collider experiment when you have just to solve high occupancy. And this detector is not magnetized, so cannot tell the charge of the lepton which comes out of this interaction of charge current interaction. So you need a spectrometer behind that, which tells you the charge and also measure the momentum, the rest of the momentum that all escaping muons from there. And this is TMS. At the beginning, when we thought we were richer than we are, we wanted just to put in what we will put in the phase 2, which is NDGAR, a detector which was a bit more sophisticated than TMS. TMS is done by slabs of magnetized iron with a layer of strips of scintillator, which nevertheless are doing their job just to making charge and measure momentum by range. The fact that these 2 detectors can move coherently and by 30-meter transverse to the beam will allow just to explore all the energy of the distribution in chunks. And this will be fundamental just to keep under control the scale and just to project the flux 1,300 kilometers distance. The other thing, the other component in there will be sand. Sand is the detector which will stay on axis and is a composition of recycling a successful experiment which has completed in Italy, and put it inside the volume which was before occupied by a large tracker, probably the largest drift chamber ever built, which was perfect, but exactly what you don't want for neutrino, because was the lightest drift chamber ever built, using aluminum wires, using helium as gas inside. So for neutrino, you would have a neutrino interaction with a new concept in which our Indian colleagues have worked. This is the experiment. You see it here. Is a large solenoid, 0.6 Tesla, inside iron yoke, which can be opened autonomously without the use of external gears, which is mounted on wheels and can move around if needed, and which contains a scintillating fiber, lead scintillating fiber calorimeter, hermetic, which is covered 4 pi because it has a barrel and 2 end caps, and this leaves a volume inside of about 45 cubic meter, where you can put a tracker and some other objects which I will describe. The calorimeter is one of the strong points of this detector because it's still the best sampling calorimeter built for electron and photons. It has a resolution of the 5.5% of root E, but especially it has a fantastic timing resolution. It has better than 60 picoseconds, and this is not on prototypes. These were the result of the experiment over all the pi. The 135 picosecond of constant term, most of them are coming from the bunch length of the DUNE machine. And it has been, the other good thing that this calorimeter has, it has a very high efficiency for neutrons, which comes very useful for one of the things for which we need just to work. There is a lot of activity because we have just to take this object, dismount it, refurbish it, because nobody has any longer the spare part for the electronics that we are using. We are putting new electronics and qualify it, because you have just to move it from a different standard to another standard. And there is a lot of activity going on together with Fermilab, and then put it on ship it over and remount it at Fermilab. And we are progressing pretty well on that. And the things are going on schedule. Essentially, we could be ready just to send most of the stuff already by the end of next year, which is too early. What we are putting inside is also a thing which was coming up in the discussion, is a tracker which has just to be light enough, but not too light, is a target tracker. Is essentially a sandwich of thin targets and very light tracker many times, repeated many times, in such a way that you have enough mass for having enough statistics of neutrino interaction. And if you are smart and you're choosing these targets in the appropriate way, you can do a very peculiar thing. You can think that you can measure factorize the flux and the cross section, because you're measuring the interaction on the not on a nucleus but on a nucleo. And there is a lot of work going on, because the two technologies that we have chosen, there is a baseline one, which is based on straw tubes, and people here has spent already enough time. And we are doing prototypes. We have done prototypes which are not as big as the final one, which will be order of the biggest one, 3.5 meter by 3.5 meter. Now we are, but all the technologies, just to test the technologies, they are very good, and the precision and the construction sequence. And we are doing the similar thing also for, in case that we go with another decision of a drift chamber, which is a sort of flat straw tube, because it's done. Then we thought also that since we have a magnetic spectrometer, would be nice just to have inside this detector a small amount of liquid argon, because you could look at interaction liquid argon happening inside this liquid argon and analyze them with the power of your spectrometer, which could be a good way in which you compare with what LAR, the argon detector, does. And so we are building a small cryostat, and we don't want just to put a drift, a TPC inside that for the time being. We use the fact that it's small, and we are reading it, we're taking pictures, because the liquid argon is a pretty good scintillator. It produces about 40,000 photons, unfortunately, in the vacuum ultraviolet per centimeter. So if you put in cameras in which essentially you can either use a lens or an Hadamard mask, and as a film use silicon photomultiplier, you can take a picture of these events, and is a nice way in which you can tell this. And then you have all the rest of your detector outside, just to measure the things which are coming out. So when we analyzed the potentiality of this sand, we could see that it could do really very many things, dearly needed, and give a lot of redundancy. It's not only staying always online and being a very powerful spectrometer could tell if something changes in the beam, because one of the things that you have just to control is if the beam parameters, which you suppose for all your work in, they have just to stay stable, and experience tells that they are not. So there should be a monitor which on a reasonable fast scale tells you the subtle changes in the beam. We would like just to provide independent measurement of the flux. The beam is not pure. It has any beam, the neutrino mu beam, that what we call forward Horn, has a contamination on the anti-nu mu, nu e, and anti-nu e. And it's important just to know this contamination because, again, if you want just, for instance, just to use the fact that you want just to study neutrino electron scattering, if you don't know the contamination and you cannot decouple it, you'll never get done. It will help just to remove degeneracies for many instances because we can compare what the prism will tell us with what you can do online. So is a good thing. Here there are some of the idea. You can see here the idea of the straw tube. There are these thin targets, and these targets are very good because being done by polyethylene, which is CH2N times, and having from time to time pure carbon, you can subtract what the interaction in this target. So it's very easy just to find decouple the targets because you have a target, you have a tracker in the middle, you have the other target. So you know the target are 5 millimeters within the square root of 12 of 5 millimeter. You know that you were in the carbon or in the polyethylene because in the middle you find nothing. So you decouple this event. And then with an analysis which exploits the fact that every time you have an event on hydrogen, you can reconstruct all the kinematics and it should be closed. In the other case, you will have the fact that you have a nucleus. So you will have, for instance, a remaining transverse momentum, but there will be an overlap region. And the overlap region you subtract by having exactly a pure carbon target. In this way, we call it solid hydrogen. I give you some example of what we can do, for instance, in the tagging of the beam, or what we can do exactly in this, with this, in which we do the shape, the flux, in the case of the forward, what we call forward. So in the case that you have a nu mu beam, and you look at the final state in which you have a muon, a proton, and a pion, and in the case that you have the anti-nu mu beam, and again, you use there the fact that this is particularly beautiful because your final state will be two-body. So it's totally close. You know the direction of the incoming neutrino. You measure the muon. You know where the neutrons and what energy this neutron should have. You go and look in the calorimeter, which is fine-grained, and you see, is there a signal of a neutron here? If there is a signal, you use the time of this signal, because neutrons are slow, to reconstruct the energy, the momentum of this neutron, and you compare with what you have calculated. And in this way, you make a very clean sample, and you end up with pretty good in the region where we are interested, which is here. You have already, after a couple of years, a pretty good. No, this was exaggerated. Okay. These are a way in which we reconstruct events in this grain, in this, when you start with an experiment which is called DUNE, you are damned, because then immediately after, so what is needed for doing DUNE? Sand. You need sand for doing DUNE, and you do sand. What is needed just to do sand is made of grain. Now we stop there. I told the people that I will change experiment if they keep going into these type of things. But these are two ways in which we can reconstruct events. One based on this Hadamard mask, which is essentially a coded mask, which is used in astronomy, which has the advantage that you can have very compact optical systems, because the focus you can decide how just to do, and essentially you don't care about the wavelength, because it's essentially holes made in and the other one is done with lenses, which are more performing, but they occupy more space, and we will design, probably the final design will be a mix of the two. To conclude, I think that today has demonstrated that there is a lot of interest in this in India. We are very happy just to have come here. It has demonstrated that we have shown that it's not a project, is happening. Is happening. And also, we have told you that there is ample space for your community just to contribute. And we are pretty sure that DUNE will be in the next 20 years or more one of the best places where we can just get fun with our searches. Thank you very much.
Talk. We have a very quick questions. I'm sorry for we have slightly overrun the time. Any questions for both the speakers?
Sorry, what is it? No, the beam direction. Now, if you can just explain briefly, why do you steer the beam?
Mainly to make the neutrinos flow through the matter.
Yeah, okay.
If you look at the oscillation probability in the spectrum, it's very different with the vacuum versus matter. And, the matter affects, the perceived symmetry, right? It plays a big role. Like I showed in one of my slides, you have this forward weak scattering. And then, those interactions would allow you to enhance the normal hierarchy, the inverted hierarchy at the same time. If you have enough baseline, you also become sensitive to the CV symmetry. You break the degeneracy. The baseline plays a key role in breaking the degeneracy. The matter effects play a key role in bringing up the differentiation.
But you want to just to see why you do this thing. That is simply is for money, for the money, because if you need just to make a very long decay chain, the angle in which you have just to do it is fixed, because it's fixed by the distance. So it's about 5.5, 5.7 degrees. If you start from the surface, and this thing becomes very deep, and very deep becomes very expensive, because then you have just to make, now our near detector hole is at 60 meters underground. In the other case would be much more. And then.
Understood the question. Yeah.
Also, one quick. So, Sergio, I think looking at your slide video, talk about the process of using DUNE or for sand, do you think we need to build a neon detector as well?
I think that we'll need we might have one already, because we we built the top CRT for Icarus, which is 400 square meter of two-layer scintillator. Maybe that we can recycle that, but we should think about it because, I mean, it's a simple detector we have placed just to put it because there is space on the yoke.
Here's even one question. And we concluded a couple of layers of the RPC.
Oh yeah, absolutely. Is enough just to tell you whether it was, yeah.
It's also the CRT from microphone.
Yeah.
There's a lot from SPN that will be able to be processed. Just want to quickly say for the students and postdocs in the room, as Sergio and I have tried to communicate here, it's a ton of opportunities when it comes to you, both in terms of, whether you're interested in analysis or reconstruction, machine learning, hardware, R&D, there is plethora of opportunities. You should talk to your PIs. I know TAFR has, was involved, is looking to get involved. But you should talk to your supervisors and the faculty to try, if you're interested, to try to get involved.
With that note, I'll thanks very much once again our speakers for a wonderful lectures. I'll request everybody to please join for the film. Thank you.
One quick, we just wanted to take a couple of minutes to thank our host. Is Gagan here or did Gagan leave already? Oh, there you go. So don't leave, Gagan. So if you actually come to the front, we just want to take a moment to thank you. Just a small token. Yeah. Well, we have something, so. So both Gagan and Bipul invited us here and, gathered the PIs from India, faculty from India, those interested in DUNE, and hosted this workshop. So we're actually very excited to be here, and we wanted to take a moment to thank. I'll thank Gagan, and Sergio will thank Bipul. Thank you, Gagan.
So, like this? Yes. Thank you.
Yeah. Hold on.
Great. Yeah.
Thank you. There's copy of it.